so I will make some stupid mistakes. Destitution will call me out for those because, yeah, he's probably not brain dead or tired. So just putting that out there. Okay, let's get started. I have a couple questions here initially. So this is just from the practice midterm. Okay, we have SRAM, and we have a chip with capacity 64 K times 8. The key thing that you have to know for this part of the midterm is basically this kind of simple formula. We're going to take this value and we're just going to break it apart to what it actually means. So this is 2 times, or 2 to the power of number of addresses. That's probably spelled wrong. Times the number of bits, or number of data lines, or number of functions, or size of word. I write all of these down just to show you they can ask it in many different ways. You kind of just have to know what it would mean. So for this question, how many data lines does it have? We look to this number as our solution, 8. How many address lines does it have? We have to break apart the 64K into the correct value. So we take the 64K. We break it apart. We have the K value, which is 1,000. We do 2 to the 10 times what? We have 64. Okay, so we know that 2 to the 3 is 8. We know that 8 times 8 is 64. Therefore, we know that it's 2 to the 6. That together, using exponential laws, would be 2 to the 16. That is our value. So we have 16. Now, what is its capacity expressed in bits? It's just telling us in total how many bits do we have. With that value, we take these two and we just combine them. So we have 2 to the 16. We know that we have 8, right? Number of bits. So this is number of bits and number of data lines. These are like the two things we're using. So we times it by 2 to the 3, which equals 2 to the 19. That is your value for this. You can expand it by taking off 10 from 19 and putting K. Then you have 2 to the 9K. And then you can expand that further if you do some multiplication. I don't know what the value this is. We won't have a calculator, so this is something you do at the end of your exam when you have time. I don't think it would be really necessary, but I'm not the professor, so I can't say. Is everybody comfortable with this type of question? One more thing I'll iterate before we start. We have like another sort of formula. This can be variables too. Just gonna put that out there. So whether they say address lines or number of addresses or variables, it's talking about this value that's above there. Whether they say size of words, number of bits, number of data lines, or functions, they're talking about this value. Alrighty, I'm going to check the chat pretty quickly just to make sure if anybody has questions, feel free to put it in review questions or car related. Alrighty, no questions. Perfect. If those haven't yet, interact with the announcement. But yeah, it's not really necessary. I will move on. Is everybody good with this? Alrighty. Now, this is the second part to this question. Using D flip-flops, design a 3-bit gray code counter which has the following counting sequence. Okay, whenever you see these types of questions, break it down into a truth table. That is always your first step. Let me get a straighter line. Perfect. 0, 0, 1, 0, 1, 0. And gotta go down a little bit. Okay, that's enough. Okay. So I'm just going to name these arbitrarily Q2, Q1, Q0. And now we have, this is the present state. Let me do P. We are going to work on the next state, which is dictated by this image. So let's just start in the beginning. At 0, 0, 0, we go to 0, 0, 1. At 0, 0, 1, we go to 0, 1, 1. So you just write 0, 1, 1 right there on the next state over. This is 2t, this is q1t, this is q0t.
I would recommend copying the order of the question rather than just going through it numerically, because it's slightly more confusing when you just, do it arbitrarily.
To be honest, I prefer this way because it's rare to mess up if you're going through that, whether you're going through it sequentially. Like in my opinion, you can do it both ways. It doesn't matter as long as you get it filled in properly. But now we're going to work on 0, 1, 0. It goes to 1, 1, 0. We're going to go here. We're find the number within the list right there. It goes to 0, 1, 0. We find it in the list. It goes back to 0, 0, 0. We go to 0, 1, 0 right here. Goes to 1, 0, 0. Then we go to 1, 1, 1 right there. We go to 1, 1, 1. And then we follow 1, 1, 1. It goes to 1, 0, 1. We're using D flip-flops. And the characteristic table for like D is it's equal to T plus 1. So it's equal to the next state. You don't really have to do any weird table rules where you match it. You just copy it directly, which I will do pretty quickly, hopefully. This is 0, 1, 0, 0, 1, 1, 1, 1, 0, 1. Okay, so this is now D2, D1, D0. Next step is forming your K-maps. We have Q2, Q1, Q0. Another important thing is make sure you always count down, or you follow like the same counting pattern that you use for the K-map and the truth table. If you follow a different pattern, you will mess up. So we got 0, 0. This is 1, 0, 0, 0. Did I mess up? 0, 0, 1, 0, 0. This is a 1, 1, 1. 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. Following this list, D2 is now equal to, this is Q1, then this is Q0 prime, plus this is now Q0, and then this is Q2. Perfect. Now we do the next. We keep that formula somewhere tidy and that where you can see it. I'm just going to do it at the top ledge here and save some space so I can just look at them both at the same time. Sure. 0, 1, 1, 1, 0, 0, 1, 1. This one would be sure. We would form this as a full group, which would be, this is Q2, Q1, Q0. This would be Q1 plus, and then you would form this as one group, which would be Q2 prime, and then this would be Q. Did I copy this wrong?
Oh, you added an extra 1.
1, yeah. Which is the extra ones. This is supposed to be 0. Okay, that makes sense. Because low-key, I was like, that does not seem correct. Okay. Okay, so then this would just be Q1, Q0 prime, plus this would be Q2 prime, and then this would be Q0. Okay, this is now D1, and we got to get D2. Should have saved some space. That's okay. It's 1, 1. Okay. Okay, we have 1, 1, 0, 0, 0, 0, 1, 1. I'm pretty sure. Q1, Q0. So for this one, 1, 0, 0, 0, 1, 1, 1, 1, 0. D0 is equal to Q2. Q1 plus Q2 prime, Q1 prime. You can also write this as Q2 XOR Q1 prime. Perfect. Give me 2 minutes to move this. Oh, this is the same question. I just copied it twice. Perfect. Alrighty, we have our 3 equations. I'm going to copy D2 down here, just so it's easier to read. Q1, Q0 prime plus Q0, Q2. Now all that's left is drawing your D flip-flops and connecting the equations to there. Perfect. So how it works, you have 3 D flip-flops. I'll do the last one. Actually, I'll just zoom out a little bit more if I can. Sure. You have 3 D flip-flops. All these D flip-flops are connected by a clock. See, clock. You have D0, D1, D2. Outputs, Q1, Q0, sorry, Q1, Q2. With your inputs, you just follow these equations. The professor actually wants you to draw the diagrams. Just gonna do this so you kind of know what I'm gonna do, but I'm not gonna do that because it's time consuming. I'm assuming you guys all know how to do this. Speak now if you don't, because that would be a big issue. If you go to an exam and you don't know how to write a circuit or write whatever circuit, sure. Then this is Q2. You just copy those equations. 1 Q0 prime plus Q2 prime Q0. This one would be D2, which is Q1 Q0 prime plus Q0 Q2. Perfect. That question is done. Does anybody have any questions for it? Anything at all before I move on? Alrighty, checking call related. Wasn't 2 to the number? Yes. Yes, exactly. If I went up here, it's written It's written right here. 2 to the power of number of addresses or variables. I'm just writing all the formulas together, so you only really have to know one thing. Okay. Nobody has any? Sure, what's up? Honestly, no clue.
It's called a gray code counter because between each consecutive term, there is only a difference of one singular bit being changed. That is what
Oh,
defines a gray code counter.
thank you, destitution. Is there something called a red code counter, or is that non-existent? Alrighty. Anyways, we can move on. Now, this is probably one of the things that is most important that we cover today. How to write a multifunction. Design a multifunction register, basically. I'm just gonna probably go through this relatively quickly. And if anybody has any questions, please feel free to shout them at me. I'm going to save some space, so I'm going to do this pretty small, or as small as I feasibly can. No change. This is I'm just copying it from here. It's just pretty helpful. Okay, this is Q minus 1. This is Q plus 3. Okay, for no change, it's better if we draw this now. Okay, we're going to be using D flip-flops. So this is D2, D1, D0. Basically the same kind of format that we did above. This is the clock. They might say, put it on a positive clock stroke, or put it on a negative clock. I'm pretty sure negative clock, you just put a bubble.
I think it's clock edge, not clock stroke.
Clock edge? Oh, okay. Well, that makes sense. Okay, when it's a negative clock edge, bubble. When it's not, no bubble. Just keep that in mind. And then this is Q0, Q1, Q2. Perfect. So for no change, we connect these to a mux because this is just a relatively simple formula for how you make a multi-register. You have 4 different variable inputs that can be sent into the D to be kept. So I'm just going to write some of the mux. 1, 2, 3, 4. Perfect. 1, 2, 3, 4. Sure. For 0, we're going to feed into these the enablers, which is M and N, and we're going to feed it into all of them, M and N. For 0, we have no change. That means that the state does not change. So Q0 just remains at Q0. So we're just going to write Q0 here. We're going to write Q1 here. We're going to write Q2 here. So we feed it into the same. That means there's no change. Even if D gets loaded, it still remains the same value. Now for the input, we have a couple inputs. So Q1 or Q0 would now be input 0, and the rest will follow.
Looking at this question, I don't think you should be using 4x1s. I think you should be using 2x1s and adders.
I'm pretty sure it's 4x1s.
I think it's easier with 2x1s and adders because addition
If you
is
want,
a pain in the ass.
you can do your own solution and post it later. But I'm pretty sure using mult is like what he taught in class. And I'm just going to follow the teacher's instruction because if you do something weird, he might dock you marks. Okay, we've done the first 2 in under like 2 minutes. They're probably going to remain the same. No change in loading external inputs it's like the most common ones for this type of question. The last 2 are variable. We have decrement by 1. That means we're just counting down by 1. So this is basically a down clock, which we've encountered before. So this is 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 0, 1. I'm going to run out of space. Oh, Lord. Perfect. 1, 1, 0, 1, 1, 1. Kind of cursed. That's okay. We're just going to count down. The best way to start whenever you have like something like that's addition or you're just adding by like a weird number, you can start at 0 and just put that number down and then count up sequentially. But for this one, since I'm decreasing by 1, I'm going to start at 1 and just go 0, 0, 0. That way, I can just turn my brain off and recopy just the normal structure that I'm used to. This is 1 0 0 1 0 1 1 1 0 1 1 1. That simple. If it said decrement by 6, I would start at the 6 and write 0 0 0 and then 0 0 1 and then continue on with that pattern. So this is the next state, which is whatever. Perfect. Then we do the D. Since the D is the same as the QT, I'm just going to leave no D and I'm just going to use the QT because I'm kind of running out of space. So this is our first equation. We have 1 0 0 0 0 0 0 0 0 1 1 1 2 Q1 Q0 0 1 0 0 0 1 1 1 1 0. Perfect. Q2 or D2 is equal to 0 0 0. So that's Q2 prime, Q1 prime, Q0 prime plus you have to form two groups here. So it's Q2. Then it's Q0 plus Q2. Then it's Q1. That formula would go right here. You just got to connect it to the second input. So when M and N are 1 and 0, this would get activated, and this, whatever this would equal to, would be loaded into D. Then you would do the same for D1 and D0. You would draw the K map. So I'll just do the first two and then leave the third. It's 1 0. This is 0 1. Perfect. 1 0 1 0. You would form this as a group, and then you would take the two corners, form them as a group, and then leave this one on its own. So this is 1 1 1 0 0 0 0 1 0 1. So this would be Q1 prime Q0 prime plus this would be Q1 Q0 Q2 prime plus, and then you just take these two corners. This would be Q2, and then by taking these two corners, you would have Q0 prime. So this formula for D1 would be, maybe I use a different color just so you guys can see where I'm leading this. Take it through here, all the way there. And then you would do the same for the spot with D0. You would find you take this, make a K map, find the equation, and then line it up there. To get full marks, as Fatty said, you have to draw the circuits. So it might take a little bit more time, but it is totally possible to solve for. For increment by 3, I'll just draw the truth table for this, because I'm sure unless somebody speaks now that needs help on K-maps, you guys will be able to like solve for it. 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. Okay, we're adding by 3. The best spot to start is at 0. I can just do 0 1 1 because that is 0 plus 3. And then after that, I just follow the pattern 1 0 0 1 0 1 1 1 0 1 1 1. Then I go to 0 0 0 0 0 0 1 0 1 0. And as you see, it cycles through the whole values. So this is present state, next state, Q2, Q1, Q0, Q2T, Q1T, Q0T. And then after that, you do your D's, you find your K-map, you get your equations, and then you link to 3 on mux. And then that's it. You do it for each. So as you see for here, the equation for D2 is linked to D2. The equation for D1 is linked to D1. The equation that we could have created for D0 is linked to D0. And then that's pretty much it. That's your multifunctional register. I'm going to check the chat for any questions. If you have any questions, write them down now. If you want me to go over anything, please say so now. Yeah, for sure. Okay. Do you want me to break it down into steps or? Okay. So it depends on what they give us, but I can go through like the basic understanding of it. We have a D flip-flop. Flip-flops act as like a holder of an integer. So it's how we like store something. The register needs to store values, and we dependent on what we input as our enablers, we want it to store different values. So they provided us two enablers, which is M and N. Why we use a mux? This flip-flop could be a D, it could be a JK, it doesn't matter. It just needs to store a bit value. Why we use a mux is because we want this register to hold different values dependent on what we set our enablers to. We want it to have multiple functions, basically. That's why they call it multiple function register. So when M and N is 0, like in the mux, which has been taught in ITI 100, when it's 0, 0, the enablers will set 0 active. 0 will be loaded into the D. So whatever values 0 is connected to will be loaded into the D and held there. When M and N is 0, 1, it switches this one off, turns this one on. Whatever value is stored there will be registered into the D flip-flop, and so forth with the rest. Does that kind of explain it? Perfect. Always remember the clock. You will lose marks. Trust me. Okay, I know somebody was typing in the chat. What was the second chart for? Perfect. Second chart was for the increment by 3. So in the question, they asked us to decrement by 1. That means count down by 1. And they also asked us to count up by 3. So where is my thing? Right there. Decrement by 1, increment by 3. So I had to make 2 truth tables because these are multiple functions. Whenever they give you something that's like not very apparent, like no change or loading external inputs, just go right to the truth table, save you some time. Perfect. Alrighty. Does anybody else have any questions? Was that cleared up, Nicorette? Hopefully I said your name correctly. Thank you. No problem. Alrighty, moving on. I think the next thing is floating point. I'm going to zoom this in a little so you guys can see it. Okay. 2's complement representation is used in an 8-bit register which contains the binary value 110110000. What is the decimal number stored in the initial register? Okay. We have, let me get black because black is readable. We have this register. That's too far out. I'm just going to write the numbers. Pretend this is in a box. We have a register that contains this value. We know that this value is going to be negative because this is a sign bit. So negative. Therefore, we can just initially write a negative here because we know it's going to happen. Then, since this value is negative, we want to get like the actual value So we take the 2's complement to turn the negative into the positive to get the value for a decimal. So taking the 2's complement, just to remind you guys, you go count the zeros until you get to the initial 1. After that, you do 1's complement for the rest. By 1's complement, I mean you switch the 1's to zeros, the zeros to 1's. So it'd be 0, 0, 0, 1, and then you start flipping them. So the next one would be 0, 1, 0, 0. And then we convert this to binary as before. This is 2 to the 0. This is 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, and then 2 to the 5. We can see here that 2 to the 3 is on and 2 to the 5 is on. We know that 2 to the 3 is 8. We know that 2 to the 5 is some value, 32. Yeah? Anybody? Sure. And 32 plus 8 is 40. So that is our value in that is initially stored. So this is our answer. Does that make sense for everybody? Dude, destitution, this is more complex than what I solved it for. But thanks for doing that. Somebody might appreciate your hard work.
Really not that more complex.
Sorry?
It's not that much more complex. It's
That's
just
it.
that it's not labeled because
That's
it's
all
an
right.
actual circuit.
Fair enough. The person with the question. I would assume it's always signed because it's held in a register. But, you know, maybe you can convince a TA to actually answer that on mid-exam. Okay, what is the register value after arithmetic right shift? For arithmetic right shift, you take the sign bit and you add it to the left. Or I will visually show you right now because left and rights are fucking confusing when you're tired. So, the arithmetic right shift, this is left, this is right. We're going towards the right. So we're shifting all these bits towards the right. So it'd be 0, 0, 1, 1, 0, 1. We keep the sign bit, and we take the sign bit and we duplicate it. And we add it there. So we take the sign bit, add to left. That's pretty much it. Give me the result in both binary and decimal. This is a negative value. We do the same thing as above. Negative. Then we take the 2's complement. It's 0, 0, 1, 0, 1, 0, 0, 0. What is this value? Well, it's 2 to the 3 plus, did I take this right? 0, 1. No, it's not 2 to the 3. It's 2 to the 2 plus, this is 2 to the 4. That's 4 plus 16, I think. 4 plus 16, which is 20. All right. You probably know from class that arithmetic right shift divides the value by 2. And arithmetic left shift, which you will see shortly, multiplies the value by 2. That might be important for the ALU, which we will cover next. Starting again from the initial number. Determine the register value after arithmetic left shift. This is left shift. So left shift, we don't take the sign bit. Instead, we add 0 to right and shift. So we have left, we have right. We're going towards the left. So we're shifting all the bits towards the left. So this is 1, 0, 1, 1, 0, 0, 0, 0. What is this value? You can do this yourself. It's negative. You take the 2's complement. Same deal. Since I know that it's multiplied by 2, I'm just going to multiply 40 by 2, which was our initial value. So it's 80. He might want to see I'll just do the 2's complement and pretend I got 80 without doing the math. So we know it's negative because of this sign bit. Then we take the 2's complement, 0, 0, 0, 0, 1, 0, 1, 0. We get this value, you get negative 80. Perfect. What arithmetic operations are performed by these shifts? As we saw above, not that far above. Arithmetic, left shift, times by 2. Arithmetic, right shift, divides by 2. Perfect. Is there any overflow? We answered this question actually in class. No. It's due to how the registers are built. So when you divide by 2 or multiply by 2, the value is always going to stay within the bounds. And we can calculate the bounds by doing so. We have 1, 2, 3, 4, 5, 6, 7, 8. 8, and we are using sign bits. So the formula for the range is 2 to the n minus 1. 2 to the n minus 1 minus 1. Our n is 8, so it's negative 2 to the 8 minus 1, which is 7. 2 to the 7 minus 1. And we can just talk a lot. Most likely they'll mark it correct if you just put a lot of words down. And you can say like, oh, only falls in range.
Hey, Joey,
Yeah?
there is actually overflow in the arithmetic shift left.
Really? Oh,
Yeah,
fuck.
There is, yeah, no, it can go from positive
Oh,
to
it can go
negative.
0. Oh, fuck.
It
Okay.
doesn't in this case because there is no
Yeah, not
sign change. That is the
in
easiest way to check for an overflow.
this
Is you look
case.
for a sign change.
Yes. So the actual formula for it, which you might need to put down depending on the question, is sine x is equal to sine y. If sine x is equal to sine y and does not equal sine s, which is your solution, then there is overflow. So by saying this, this is for mostly addition, but if you do some arithmetic and this sign does not remain the same, that means there has been overflow. If it changes from positive to negative, as Destitution said, there's overflow. But in this case, there is not. Perfect.
Well, technically, I think it's called underflow if it wraps around from negative to positive.
Oh, fuck. But yeah, not in this case. Is everybody good with this?
Just a side note.
Mm-hmm.
So when you're doing arithmetic shift left, right, and your two most significant bits are opposite signs, you will have overflow.
As I said here,
Even if it enters the range.
this is the formula for it,
Yeah.
basically. But yeah, you're correct. You're correct. Is everybody comfortable with this? Like converting? Speak now, forever hold your peace. Well, not peace. You can type it in the chat. That's what you might yell at you, though. No, I'm joking. Alrighty. Perfect. Now we're going on to ALU stuff. Probably the most important thing that I will cover. Whenever you see it formed in this matrix, hopefully they don't. Hopefully they just give us a table and save me some time. I can't read it like this. I don't know if you can. It's not in a way that I'm familiar with, so I'm going to just rewrite it. Might take me an extra minute on the exam, but I will save it in terms of getting it correct. This is 1, 0, 1, 1, 1, 0, and then underneath it is 1, here, let me zoom out just a tiny bit. Or that's better. 1, 1, 1. This is our f. We go a plus b. We go a plus b plus 1. I'm just copying it directly from here. We have a plus b prime, a minus b, a plus 1, a minus 1, a complement plus 1. Perfect. All you have to do is break it down into its parts. And while you're doing this, you want to try to force a relationship because the full adder takes 3 inputs. So no matter what you need to do, you need to force 3 additions within this whole like table. So you can do it as so. A plus B would be A2, A1, A0 plus B2, B1, B0 plus 0. And then the next one, you just do the same, A2, A1, A0 plus B2, B1, B0 plus 1. Okay, once you established your first 2, you want the rest to follow kind of the same relationship. 0, 1, 0, 1. So the same thing as Z. So you kind of have to force it sometimes. Sometimes they give you weird equations, and you have to just either add 1 and then subtract, or minus 1 and just try to force it. I'll give you some more examples near the end on how various ways you can do that, but let's just continue forward. A2, A1, A0. Now we're just adding to the complement. B1 prime, B0 prime plus 0, and then minus. So if you take the complement, 1's complement, and you add 1, it's the 2's complement, which is a relationship we kind of learned in first year, but we delved deeper into this year. 2's complement is negative. So whenever you have like a minus, b minus 1, you always want to try to take the 2's complement because that's how you subtract. So 2, a1, a0. That's why we do the prime on the b's and we add the 1 at the end. Therefore, this turns it to negative b. Then we have just a0 plus 0, 0, 0 plus 0. And then we have a plus 1, which is just the regular copy the same from above, plus 1. Okay, now we have a minus 1. Like I said before, whenever you see a minus, you want to kind of take the 2's complement. 1 is as follows, 0, 0, 1. Taking the 2's complement of this, we go to the first one, and then we do 1's complement for the rest by switching the zeros to the 1s. So it'd be 1, 1, 1. So instead of, here, let me just do this. The first part, instead of minus 1, we're going to add it by the 2's complement, which is 1, 1, 1 plus 0. So we still keep that relationship with the z. Okay, now we have a prime. So a2 prime, a1 prime, a0 prime plus 1 plus 0, 0, 0 plus 1. Okay, you might be thinking to yourself, usually when you do this type of equation, these two always match in terms of x and y. Or I'll use different variables since x and y is used there. P and Q. They're always matched. But for here, you can see there's a little difference. We will solve that when we draw it out. So let's just work on the first two. I'm going to draw the general layout for how you will answer this question. And then I'll show you what happens when you have like a weird ending or a weird equation that you have to kind of draw or account for. So I'm going to switch to black again. So it's the same thing. We have the flip-flops, pretty sure. I might be misremembering, but I'm sure we just keep it with D. I'm hoping somebody corrects me because I'm used to writing D, so I might be mixing it up with another thing. We have the clock, which is down there. Let me just put this down a little. Perfect. And we connect this
I
to
think
a
it's full adders.
Oh, full adder. Thank you. Oh my god. I knew it. I was okay. Full adder. Whoever that was, thank you so much. Everybody else was just watching me fail. I'm joking. Totally joking. Okay. Full adders. I don't think full adders take a clock. Okay. I was just writing these. I'm gonna stir it over. And hopefully maybe draw it neater. Full adder. He does this symbol for the full adder. They're interchangeable. As long as they know what you're drawing, you're good. Perfect. And then this is the output. For the full adders, we have a C out, which leads to the next full adder, which goes into the C in, just to let that be known. And as we say here, this follows the relationship of Z, because Z goes 0, 1, 0, 1. This goes 0, 1, 0, 1. So we're going to feed for C in, we're going to feed in Z. Perfect. Now we're just working on the two other inputs. So we're going to have two muxes for each of these, because depending on what the values of X and Y are, we're going to add together two different things. So I'm just going to do the first couple. So this will be relatively simple. So this is a mux. We feed in here. We're going to feed in all of them, X and Y. Okay, we're going to work on P first. Let's just say this is P, this is Q. Doesn't really matter. You don't really have to name them. I'm just writing it so people looking this over will kind of know what I'm talking about. This is A. Okay, I'll just say this is Q0, Q1, Q2. This is A0, right? Because these two are A0s. These two are A0s. These two are A0s. And the second one is weird because it can be A0 or it can be A0 prime. Whenever you have something that's different, try to see what you can relate it to on this side. So I'm just going to highlight this one as being different. And I'm going to just put this there. A0 and then A0 prime. Well, what relationship does that follow? If you look across the table, whenever Z is 0, we go with A0. Whenever Z is 1, we go with A1 or A0 prime. So we're going to actually, instead of connecting this to a single value, we're going to connect it to a 2x1 mux. And we're going to feed in Z. We're going to connect A0 and A1. That way, when Z is 0, it will take the value of A0 and put it into the full adder to add. So it will follow this part. But when Z is 1, it will take the value of A0 prime and it will feed that in instead. And then it's going to be the same type of thing for the rest. But now let's focus on Q. Okay, Q is relatively simple. We have B0. Two B0s up here. You can't really see my my thing, but let me just perfect. We have B0s here, so we're going to write B0. We have B0 primes here, so we're going to write B0 prime. We have zeros here, so we're going to write 0. And then we have ones and zeros. The second you see two different values, you go to the table and you find the relationship to another value. See what you can do to switch them. So you can see it's 1, 1, 1 when Z is 0. 0, 0, 0 when Z is 1. So we're going to connect Z prime. Or we can connect Z. Let me think. Okay, I'm just going to connect. Oh, no. we can just connect z prime here. Yeah. Oh yeah, we can just connect z prime here. Why I'm thinking this is because when z is 0, when it's 1, 0, or when it's 1, 1, 0, 1, 1, this end will be activated since x and y is equal to 1, 1. That means it's 3. 3 will be activated. And then it would take the value of z prime and add it to the full adder. The value of z prime when it's 1, 1 will be 0. But no, because when it's, oh no, that's good. And then when it's 1, 1, 1, this 3 will also be activated, but it will take the value of z prime, therefore adding 0. Does everybody understand kind of that? I'm going to check the chat. Does everybody understand like why I just put z prime there instead of a mux? It's because it follows the values of z prime. Perfect. Just nobody speaks up, which is good. And then you do the same thing here, but for A1, you'd put A1, A1, A1. You would connect this to a mux. To be honest, you could probably, yeah, just gonna connect it to a 2x1 mux. We're gonna feed A1, A1 prime to a 2x1. And then we're gonna enable it by Z. And then it's the same thing here. Should have wrote it with space. Yeah.
Hi, sorry, I missed a bit of it. Why are we connecting A1 and A1 prime to a 2x1 mux and then connecting that to a 4x1?
Perfect. Let me just finish drawing this and then I will. Okay. So if you look at the truth table up here, we see that the values of the values at the end are completely different. We have A2, A1, A0, and then we have A2 prime, A1 prime, A0 prime. Usually, whenever you do this question, they form relationships of 2. That's why we can use a 4x1 mux, because the two values are usually the same. In this case, they're different. How do we solve this? We need a way to toggle between these two different outputs dependent on one of the enablers that we use, because that's the only thing we have. So we look for a relationship. We see that we select for a no complement when z is 0, and we select for a prime whenever z is 1. So we connect it to a mux. Another mux connected to that input, and we connect it to z again. So when z is 0, it would take a. When z is 1, it will take a prime. So it follows the same thing. So when it's 1, 1, 1, when it's 1, 1, 1, it will take the fourth thing because x and y will be 1, 1. So it will take like the third 0, 1, 2, 3. It will go to 3. C, take this value. When it's 1 plus 1, 1, z will be 1. It will take the 1. It will take a prime and put it to the full adder. So, and that's kind of what we want. When it's 1, 1, 1, we want to add a prime. When it's 1, 1, 0, 1, 1, we go to the third. When it's z is 0, it outputs a0. So we're adding a0. That's why we needed two different, another mux, because we have just a variance and not like a 2x2 relationship. Does that make sense? Since you
Yep,
missed that,
thank
you
you.
probably missed this part too, where I added z prime instead of like
Yeah,
a. Okay, I can go through that pretty quickly. It's the
alrighty.
same thing. We're adding by two different values. They're not the same. We have 1, 1, 1, and then we have 0, 0, 0. What relationship does this follow with the enablers? When z is 0, we're adding by 1, 1, 1. Right? When z is 1, we're adding by 0. So we can connect it to Z prime. So when we activate it by 1, 1, 1, 1, 1, 1, it will go to the third output because X and Y is 1, and then it will take Z prime. Since Z is 1, it will output 0. And as you see here, whenever we want 1, 1, 1, we want to add by 0. So therefore it's correct. Make sense?
Yep, thank you very much.
Perfect. No problem. Okay. So it's just going to be the same copy and paste basically for the rest. So I just did the same for, this is 1, 1. Yeah, so this is B1. Sorry, the writing's actually very messy. And then you're going to do the same thing here. I'm just going to write it cleaner so people kind of get a sense of what I'm doing. This is 4 by 1. We have 3 outputs, 0, 1, 2, 3. We have A0, A0, A0. This connects to a 2 by 1 mux. We have 0, 1. We feed in Z. We have, okay, this is not A0, this is A2. We have A2, right? And then we have A2 prime. And then for this one, we have the same thing. All these are fed by X and Y, by the way. Just putting that out there. I'm not drawing all the details. Well, I kind of am. I'm just mentioning it. But please be sure to connect it to the enablers because that's how the mux works. If you do not, you're basically not drawing a mux. B2, B2 prime, 0, Z prime. And that is it. That is your ALU for this question. Drawn a bit messily, admittedly. I will reiterate since I think a lot more people have joined. I'm a student. I might make mistakes. The institution will probably correct me if I do. But yeah, just putting it out there. I'm brain dead and I am tired. So please forgive that. Alrighty. Next question. Does anybody have any questions for this? Or are we good?
Wait. What was the mistake again?
The mistake was instead of 1, I put it A2. Or instead of A2, I put it A1. That was pretty much it.
Okay, wait. Where did the 2 by 1 mux come in? Like,
Okay,
why are we
perfect.
using a 2 by 1?
Okay. I'm gonna actually add like another page between these two. Just so I can kind of draw it out. I wish I could, actually I can copy and paste. Give me a second. Let me just take this, put that there. Fuck. Okay, perfect. And I can scribble all over this without worrying about clarity. Okay. That is way too far. Sorry. Forgive me. Give me. Okay, perfect. So,
Wait, is it because of the zeros, like the
Yeah.
last two ones?
Oh no, it's actually because of the A. Here, where am I? Okay. You see how they follow like a
okay.
relationship where every 2 is the same?
Yeah.
As you go down, you see that this is A, this is just A, and this is A prime.
Oh, okay.
They're 2 different things, therefore you have to account for those differences. How do you do that? You go to the enablers and you see which relationship they follow. You can see here that when it's A, for instance, Z is equal to 0. When it's A prime, we want Z is equal to 1. So you would basically connect the mux to a 2 by, you would connect the 4 by 1 mux. You would connect the third to another 2 by 1 mux, where you would connect A here and A prime, and you would enable it by Z. So when Z is 0, you would take A. When Z is 1, you will take A prime. So if you just went through like the first 2, this is X and Y. Let's say X, Y, 0. Let's say it's 1, 1, 0. What value would output here? When it's 1, 1, X and Y is 1, 1. We know that we're going to go to the third output and we're going to activate it. We're going to take the information from it. Okay, the information is coming from this mux. Z is 0. So it will activate this. We will take A. So when this is the value, we will add by A. Okay. When it's 1, 1, 1, same thing. We go to the third line on the mux. We go to this other second mux, smaller mux. Z is now equal to 1. Therefore, we take the first line, which is A prime. Therefore, we add by A prime. And as you can see here, it follows that relationship. So I'm going to label this as Y 2 by 1 mux. And then I'm going to reiterate why I did a Z, because that might also be confusing. So this is going to be YZ. Why did we have Z? We look at here. They're also two different things. Alrighty. We do the same thing. We have the first initial mux, X and Y. 0, 1, 2, 3. This is the third output right here. Why did we put Z prime? These are two different values. So when X, Y, and Z, when X, Y, and Z is 1, 1, 0, we need to add by 1. How do we do this? So we just see if there's a relationship. Well, Z alternates pretty fast. So we're going to pick Z. When Z is 0, we want the output to be 1. So we put Z prime because that's what it follows. When it's 1, 1, 1, we want to add by 0. So for instance, this just works in general because dependent on Z, whatever you add by will change. Alrighty. Does everybody understand that? Perfect. I'm going to check the chat. Alrighty. One more thing. I kind of want to know how many people join. So if you have joined, please interact with the fire. Perfect. Now we will continue on. I think I have one more ALU question. Or do I have two more? Okay, I have a couple ALU questions. I'm going to do the next one and then probably take a break. And like probably officially end the session because we've gone for like an hour. If you want me to do the rest, I can. Actually, you guys pick. Which question do you want? Are you struggling with more? A multi-register question, which I've already covered initially. A basic D flip-flop question where you're counting by various things. Or are you stuck on ALUs? I'll take a little vote. I'll do one of the three. You guys get to choose, and I'll give you your choices in call related. Or, yeah. So we have ALU, multi, verse, ALU, multiverse, flip-flop. So start voting. Damn. ALU sweeping. Oh, shit. Oh, flip-flop got an X. Fuck. Multi? Damn. Can you do these, please? That's the multi, so vote for the multi and hope you win. Oh no, that's like the ALU. So vote for ALU question. And then you guys can pick between the one I have on my page and this one. Oh, this is one with the ALU and the logic unit. Charlie. I don't know why that happened, but sure. Okay.
An
voting-
ALU has a logic unit.
No,
What do you
I
think
mean,
the L in ALU stands for?
Dude, I'm talking about like the question he wants is in class, which is mostly the arithmetic. Sorry, misworded. I'm tired, bro. Okay. So ALU. Which one do you guys want me to do? This one right here, where you have decrement, increments, add with carry, or just regular add, or you want me to do the one the guy posted? I'll just put this as a vote. Guy posted. Sorry, I'm just calling you Guy. Don't take offense. Or mine. Take no offense to whichever one you choose. It's your choice, though.
Wow, you really just called the poor guy just Guy. Wow, okay.
Okay, fine.
Okay,
I'll
Zep,
rename it.
okay.
I'll rename it to
Okay,
H.
Zep. Okay, Zep.
HJ. Okay. Guy has left and right shift. Yours has the same functions. Guy because okay. So I think we're gonna do guys. Guy because it's from 2019. Okay, perfect. Alrighty. Let me get a drink of water. Alrighty. How much space do I need for this question? This page will actually be given to you guys once the session ends. I'm gonna do just let's do some graph paper. Get fancy. Let's go 2 pages right now. Okay. Fuck, don't open that. We go here. Okay. Guy, you have won by landslide. I got wrecked. That's okay. I'm just gonna open this link to see this question. God, this is the blurriest question, but I can do it. 3-bit register. You guys can see my whole screen, right? Perfect. Addition. Alrighty. I'm gonna take just this and put it here. And I'm just gonna hope I get this first try. I probably will. Hopefully. Okay, let's start. Let's switch back to black. Okay, we're gonna do arithmetic here. So we have S2, S1, S0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. When it's the same thing as what we did above, this is the function. When it's 0, 0, 0, we're doing a plus b. We're doing a minus 3, a plus 1. We're doing a minus b. Okay, let's write them out. This one is, I know this is 3-bit. You want me to do 3-bit? You want me to just do it all? Or do you want me to do 2-bit? You guys' choice. I just want to know if you guys can visualize it with just 2, or do you want me to do the full 3? I don't know what the professor did in class, but I can do either. 2 versus all 3? Okay, you're gonna put me through hell. Fair enough. Alrighty. Okay, then I'm gonna get drawn. Fuck. A2, A1, A0. Please give me space. 2, B1, B0 plus 0. This is A2, A1, A0. We're gonna subtract by 3. What did I say about subtraction? You're gonna take the 2's complement. Because this is a full adder. You're gonna need to add. Take the 2's complement so you can add by the subtraction. 3 is 0, 1, 1. Take the 2's complement. 1, 0, 1. So we're gonna add by 1, 0, 1. Then we're gonna add by, or let's just add by 0 and then 1. This is what I said before about forcing the relationship. Forcing the relationship with z. So instead of just adding by 3, I subtracted 1 by 3 just so I can add 1 with z. Sometimes you're going to have subtracted by 4, and you will have to instead subtract by 3 so you can add 1 with z. Or in the other case, you need to force a 0, you would add by 2 or subtract by 2 instead of subtract by 3. Just depends on your question. Okay, now we have A2, A1, A0. We're going to add it by 1. So we're just going to write 0, 0, 0 plus 1. Yeah, that works. A2, A1, A0. We're going to add it with, or subtract it with B. So it's plus B1 or B2 prime, B1 prime, B0 prime. And with subtraction, you take the 2's comp, or you take the 1's complement, or 1's comp, and you add 1. That's why we take B prime and we add 1. Did I do this? Actually, I'm gonna write this as, I kind of want to force a 2-2 and then 1-1 relationship. So I'm gonna think about how I should write this. Let's just keep this as what I had it before with the 3, and let's instead add 0. That way it's 0, 0, 1, 1. Yeah. Because I kind of want there to be 2 values of the same z. Okay. Or not z. I say z because that's like the generic example in my head. But we're adding by 0, 0 and 1, 1. What relationship does this follow to the truth table? Well, we can see here, when we want to add by 0, we take S1. When we want to add by 1, S1 is usually 1. When we want to add by 0, S1 is 0. So we're going to take S1 into our full adder. So this is just going to be, we're going to have 3 full adders. I'm going to write it both ways. The teacher does. You can choose which one you do. I'm personally going to write FA because that is how I kind of learned it. I'll just do 1 for now, just in case. Okay, we're going to add S1. This is, yeah, S1 into the full adder. We're going to do a mux. Let's just do what I usually do, which is a 4x1 mux. 0, 1, 2, 3. Perfect. So we see what we have to do. When it's, and then we're going to feed here. Since we took S1, we should probably feed in. Do we still feed in S1 and S0? Let's see. 0, 0, 0, 1. Yes, we do. S1, S0. We feed it into here because they alternate and they go to 4. So when it's 0, 0, we want to add by A for this one. So we do A0. And then I'm going to just do a second one here, which we probably need. 0, 1, 2, 3. When it's 0, 0, we add by B. B0. When it's 0, 1, we're going to still add by A. It's A0. When it's 0, 1, we're going to add by 1. When it's 1, 0, we add by 0. 1, 0, you add by A0 still. And then it's A minus B, you add by A0. And then you add by B0 prime. Perfect. We've done our first one. Like I said before, I'm not really looking at the solution, so if I'm wrong, please warn me now. Then full adder, or the full adder has 3 inputs, and it also has an output, C out. We connect that to the next full adder. And we're just going to do the other bit. The other bit follows basically the same relationship as the rest. A1, 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 A1. To be honest, you could probably just connect A1 here. You'd be done with it. But I'd play it safe and use a mux. This is B1. But the other two vary. This is B1 prime. Let's check back up top. When we are at 2, or when we're at 1, let's just go with 1 first. Right here, we want to add by 0 when it's the first one. So we go here, we add by 0. Now we go up. When we're at 2, right here, we want to add by, right here, we're going to add by 0. So that kind of stays the same. So it's 0, 0. Okay, we go ahead. This is Q1. This is Q0. Wow, look at how neat this one is. This is Q2. Okay, maybe I'm jinxing myself. Or maybe because I'm using a full page. We have the mux again. This is just going to be A2. Now we have the other mux. These mux are fed by, which I should probably clarify. All of these are fed by S1, S0. So it's going to be S1, S0, S1, S0. Make sure you connect them. And
You missed an S1, S0.
I know. I know. It's disappointing. S1, S0, S1, 0, and I'll do it just for you. It's gonna be messy.
Yeah.
It's gonna be messy. Fuck. There, happy? Okay.
Mhm.
Instead of doing the mux, I just connected A2. Now we go here. This one, we just follow this line. So we just see like, oh, but do we need to switch it? Literally, let me just find this. We're just gonna copy this and just put it down there. So it's 1, it's B1, it's B2, 1, 0, B2 prime. So we go here. This is now B2, 0, or B2, 1, 0, B2 prime. Done. That is your arithmetic unit. And I'm gonna lighter blue. Let's go. Where is this? Thank you. Arithmetic unit done. Woo! Now we're going on to the logical unit. I'm gonna take a picture of the same picture and write it down. Let's go. Hopefully it doesn't disappear by the time. Okay, we're good.
Wait, quick question.
Sure.
How come S1 is the
Fuck.
input for the full adders in S? Was it? We can
Yeah,
just
yeah.
scroll back up a bit.
I'll go
Okay.
over it. I'll go over it. Just let me organize this so I don't have to take a screenshot again. Okay, perfect. Yeah. So for
Oh, yeah.
S1.
Just question was like, why is
Yeah, yeah,
S1 the input and then S1, S0 inputs for the
Okay,
multiplexer?
perfect. Good question, because this is actually pretty important. You kind of have to understand the system. Okay, we're gonna try to force this relationship right there. We're gonna see which value it corresponds to between all the enablers. As we see, it's 0, 0, 1, 1. If we look across at this table, the only one that could possibly follow this relationship is S1. Because it goes 0, 0, 1, 1. If it was alternating, we'd go with S0. Sorry. If it was just 0 or just straight 1, you'd go with S2. But since it's 2 and 2, we go with S1. That's why we add S1 here, because we're adding by 0, 0, and 1, 1. For these inputs, we kind of have to force it to go from 1, 2, 3, 4 in binary. The only two that do that is S1 and S0. Because you see here 0, 1, 2, 3. And if you see in the mux, 0, 1, 2, 3. That is why we connected S0 and S1. Is that satisfying answer? Kind of?
Yeah, makes sense. Thanks.
No problem. Okay, we're going down slowly. And we're gonna do this thing, which I haven't practiced at all. So we're gonna play it by ear. We have 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Sorry, I got a cough. Whew. Let me drink some water. Give me 1 second. Ah, perfect. We have S2, S1, S0. Okay, for this one, we have a shift left, a circular shift right. Then we have A and B negated, and it just says NAND, which is weird. Maybe they want us to build it with NAND gates, or maybe this is just NAND. God. And then we have A XOR B. Perfect. So we're going to continue here. Okay. We have multiple functions that we have to implement. What do you do when you have multiple functions you have to implement? Well, you use a multiple function register. You use like the same type of logic in order to implement it. So I'm going to just do that. We have A shift left. Okay, we have A2, A1, A0. As I said before, A shift left. This is left, this is right. This is exactly what I'm going to do on my exam. Should this question occur, I'm going to write left, right. We're going to go towards the left. We're shifting everything that way. That means, and it's arithmetic shift, and it's left. That means we don't care about the bit or the sign. We just add a 0. So in place of this, we add a 0. Then we go A0. Then we go A1. Done. So this is what we're switching the values for function 1. Now let's do function 2. Function 2. We're going to do circular shift right. Okay, we have A2, A1, A0. We have left, we have right. We're going in this direction. Circular shift, we just shift it in a circular direction. A0 feeds back to the end, and then everything gets pushed up. A2, A1. That's it. We're going to switch A2 with A1. We're going to switch A1 with A0. We're going to switch A2 with 0, A1 with 2, A0 with A1. Done. We're done with shifts. Okay, what other functions do we need to do? We need to implement whatever this is, which is NAND. We know NAND is this. It's and negated. So we kind of have to just build that. Just going to write it there, just to remind me. And then we have XOR. This is the XOR gate, guys. We're feeding in A, and we're feeding in B. Okay. Let's start. What are we going to feed into our mux? What's the most reasonable? Well, this is the only two that go to 1, 2, 3, 4. So we're going to feed in S1 and S0. Let's go here. We're going to draw our mux. We're going to just draw, this is F. This is what F equals out to. This is going to be a 4x1 mux. So we're going to write 0, 1. I should probably push everything to the side. Just save some space. 0, 1, 2, 3. Boom, 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 boom. We're gonna have to repeat this 3 times, but I'm just gonna do the initial one. So this this is gonna be A0. Perfect. So when it's 0, we're gonna feed in S1, S0. When it's S, here, let me zoom out so I can see this and I can point at it. Let me just. Perfect. When it's S1, when S1 and S0 is equal to 0, 0, we want to do arithmetic shift left. And since we're working with A0, you see what A0 equals after the arithmetic shift. You see here, A0 equals 1. So we're going to, A0 is equal to 0. We put 0 there. Now we do the next thing. When S1 is equal to 0 and S0 is equal to 1, we do circular shift right. As we see here in function 2, A0 gets converted to A1. So we feed in A1. Okay, now we go next. We have this NAND gates that we have to do. I'm going to just zoom out a little bit more. We have the NAND gate. So we're going to take this 2. We're going to feed in A0, NAND it, with B0. Perfect. Whenever I write A or B, it's just A1, B2, or A2, A3. I'm just writing it in a generic way so we can apply it to most of the formulas. And then when we have 3, which is S1 and S0 is equal to 1, 1, we're going to use an XOR gate. Not that, sorry. This is A0, B0. That's it. This is, once you get the first 2, you should get all of them because it follows the same general formula. I'm going to write the rest very small because I'm running out of space. I'm going to do this in a different color so I can actually, you can see where I'm pointing at, right? It's not too small for you guys, is it? No?
No, it's okay. It's okay.
Perfect. Okay, we have when it's 0, 0. So we're doing like the same thing. The first one is arithmetic left, which is just function 1. A1 gets converted to A0. Since this is, let me just follow this. This is A1. We're going to connect it to A0. You probably can't see green, so I'm going to use a darker green. A0. Okay, now we do circular shift. A1 equals A2 at the end of the circular shift. So we're going to connect A2. Perfect. And then we do the same thing with the gate. Right here, we do an AND gate with A2 and B2. Then we go here, we just continue onwards. We do the NAND gate, not NAND gate, the XOR gate with A2 and B2. Done. Do the second and last thing. It's the same thing. We have, now we go up here, we see A2 gets converted to A1. We write A1 for logical shift left, or arithmetic shift left. Then we have this one. We go here. We see that A2 is now equal to A0. We write A0. Continue on. We do the NAND gate between A2 and B2. And then we do the XOR gate between A2 and B2. Fuck. Done. Imagine that. We have the logical unit done. Oh, fuck. Logical unit done. Woo!
Wait, Joey, I have a question.
Sure.
So is that a logical unit or LSU? So it's a logic.
It's probably whatever the question asks for, to be honest. I'm guessing it's the logical unit.
Wow. I think it has the
But-
shift, right? It has a shift.
Yeah. So
Yeah.
I'm just gonna
I think it's
continue.
just an LSU.
Okay,
both
it
of
might be
them.
LSU. I'm probably a little confused. Is somebody still recording
Yeah, but there's not gonna be any volume in the
audio?
recording.
Okay.
Yeah.
I think the person. Oh, yay! Was recording the mouse dude at the bottom of my screen.
Oh
So
yay!
I think perfect.
Yay!
We're almost done. So after this, you can find a way to send it to me or post it in the chat. Doesn't matter. Okay. I'm gonna group this up. We have, because I'm thinking the question asks us to connect it. I don't know if it does, but I'm gonna connect it anyways because why not? Hopefully, if I remember how. So the AU. Imagine this is now a square, and inside of it is AU. Okay. I'm gonna change colors just so we can see clearly. Okay, this is now converted into a square, which is called LU. Perfect. Or like 1 unit is. So we're going to connect the AU to the LU to make the ALU. Okay, we have the LU. Or fuck. We have the AU. Wait, I said I was going to use different colors. I lied. We have the AU, okay? And we're going to connect this to, I think, a 2. Here, let me just redraw this and think for a minute because low-key I don't remember. Sure. Okay. What happens when these switch? We switch from the logical to arithmetic dependent on S2. S2 is equal to 0 for the arithmetic. S2 is equal to 1 for the logic. So what do? We have a 2x1 mux. We connect it to S2. When S2 is equal to 1, we go to the arithmetic unit. When S2 is equal to 1, sorry. When it was equal to 0, we go to arithmetic unit. When it's 1, we go to the logical unit. I know in class, he had like 2x2 muxes connected to a 2x2 mux. I think it's for another unit that I have not done yet. But I'm pretty sure, just given the AU and the LU that this question is giving me, this would be the answer. So we have a bunch of wires here. This is just like a general component. It would be connected like this. If they ask me to connect them all on the midterm, I'm going to do it like this. I'm going to be like, okay, imagine this is the AU, imagine this is the LU. This is how you do it. Because I'm not redrawing this for nobody, okay? This is going to be a lot of work. But yeah, does that make sense? Anybody have any questions?
Hey, Joey?
Apparently,
Gonna-
for that, marks will get cut off. Wow, that's dumb.
For which one again? Which one?
If you don't write it, like AU, LU, like actually take the circuits and put it in here, marks will get cut. By the way, I'm just gonna put it out here. This is for 1 unit. Or like 1 bit. I'm pretty sure. So this would be like F1 or like F0. Right? And then you would have the second one, the same thing, F2. What we're connecting here, which I'll just iterate before I get questions about this. This AU part, let me just go here. This AU is actually just this. Just this. This is what's feeding into it. Not the rest, just this one. Even though the rest are connected, this Q0 is feeding into that ALU. Like this single part. For the LU, it's the same thing. Only this one's feeding in, potentially. You would have to do 3 of these in order to get the full like picture. I'm pretty sure, if I'm remembering this correctly. I got it right. It asked for logic and shift. Let's fucking go. Guys, are we switching to daily light savings? Does the midterm time change? Oh my god, is daylight savings the same day? Please tell me no.
Yeah, what's it called? If it's daylight savings at 1, only 3 a.m. repeats. So like it's still at 1 p.m.
Okay, but do we get an extra hour or do I have to wake up
Yeah,
earlier?
we get an extra hour of sleep.
Oh, thank Christ!
Yo,
Oh god,
let's
let's go!
go.
Easy. Okay, thanks for telling me
Biggest
that.
W all week.
True. Okay, anybody have any other questions?
For the final product, so
Yes.
would you just have 3 2x1 muxes with the correct AU and LU components putting in
Yes.
S2 as a control for each one of them, and then it's just F0, F1, F2?
Yep.
All right,
Well, it's
fantastic.
not really F0, F1, F2. I'm just writing it as like to differ them. You could put Q0, Q1, Q2, whatever. Doesn't matter.
So
as
I
long
can
as
put
you-
pineapple 1, pineapple 2, pineapple 3.
Go ahead. Waste your time. It's like I honestly keep it like 2 letters because you want it. Okay, this exam and like for all of the exams this year, rush through them. You might not have enough time if you don't know this material off your heart. And like I'm telling you, sometimes weird equations will occur. You don't know what's coming. So rush through the easy stuff. If you have more than enough time at the end, check through your answers. But answer every question at least. These questions are worth a lot. 30 points, 20 points, 40 points. If you don't answer one question, you have a potential to fail. So answer them all. Okay.
Is
I'm
this
sure
a
you-
3-hour midterm? Or 1.5 hour midterm?
I think it's regular
I believe
time.
it's 120.
Yeah.
Oh, that's bullshit.
Don't
I
worry.
think our CSI one is the 3-hour one then. Because
No,
I
it's
swear one
not.
of them's 3 hours. What? I
They're
swear
both
one of
1
them was
hour and a
3
half.
hours.
Alrighty.
That's bullshit.
Yay, you
Mm.
can cut the recording. Thank you everybody for coming here. This has been Zep.